Here I am in the great outdoors with my mural made out of 5 sheets of plywood that shows us how to divide the circle perfectly into 360 degrees, something that can't be done in base 10. So this is a revolutionary new geometric pattern that gives rise to a base 12 version of pi that's different than base 10. The reason I say that is because the construction of this diagram is literally dividing the diameter of that very first, well, of each circle, each ring, into the circumference of the circle. So that's the process. Those black dots there are units of the diameter being dispersed onto the circumference. It's a geometric pattern. We already know the diameter. We know the perimeter of the polygon. That becomes the circumference of the circle. The polygon is like the scaffolding for the points of the circle. We're placing these black circles on the points of the polygon. There's a space between them. That's the new idea. We're working in units of square root of 2, so it is an irrational number. The overall answer is still a square root, but there is symmetry and balance. So right now I'm in the process of showing everybody how to continue growing the diagram. We've got the initial, let's see there, 1, 2, 3 rings are all positioned. I basically run out of little black circles to keep putting them on there. But I'm going over the process. You can access all this information in my book called Understanding Base 12 Math, How to Draw the Perfect Circle Using Dozenal Geometry. It's available through Amazon. You can access, it's basically an introduction to Base 12 Math, letting you know that it is a legitimate thing. And the difference lies in the size of the decimal places. So each ring of this diagram is built in units of 0.5 root 2, which is 5/12 from a base 10 perspective, units of square root of 2. So that's our defining smallest length. So 5/12 isn't really accessible in base 10 as a decimal place. And we need those decimals in order to anchor this diagram on the Cartesian plane. So it has to be built on a base 12 Cartesian plane, or a Dozenal Cartesian plane, where the length of 1 is divided into 12ths instead of tenths. That's the difference. That's the big difference, and that's the difference that nobody's really thought about before. Those points, you can't really access them as specific lattice points in base 10. It's as simple as that, and that's a sticking point for some people. They don't quite get it. But when you have a length of 1 and you're trying to reach the distance 0.5 or 0.7 twelfths, you have to always divide by 10 first, and then you get a repeating decimal as you try to get closer to that precise point. That's very easy to get to when you've already divided your length of 1 into twelfths to begin with. So that's the main point to